So I'm going to go ahead and give a brief overview of the next topic that we're going to be dealing with, which is linked lists. Okay. All right, so we've been previously dealing with the array list, which give you one contingent chunk of memory, right? And now what we are dealing with are linked lists, which instead of having one contingent chunk of memory, each item in the list is created in a different memory location. Let me go ahead and make this bigger at first so that the recording will pick it up, right? And these little chunks of memory are called nodes. All right? And essentially they look like, we represent them like this. This will hold the memory location of some item, okay? And they also hold the location of the next node in the list, right? Which we draw like this. And then they'll also have, again, some item. And this guy will also have an X over here. Okay? And the idea here is that in a linked list, you don't really know where anything is except for the first item in the list, which we call the head, right? And more on that in a bit. But the way this works is essentially it is effectively a scavenger hunt through your computer, right? Each item in the list, each node contains both an item that's in your list and where the next item is. And again, I'm just going to be paraphrasing very quickly through the stuff that I covered in the latest videos. Okay. All right. So, and the idea here is that each of these have a next variable, right? It stores the memory location of the next node, indicated by this arrow, right? Notice that the block, right, is saying that this is stored in this. But normally, for speed and just for succinctness, so I don't have to necessarily draw everything, nodes are typically represented like this, right? Where basically they're just represented as squares that point to the next node in the list, right? So this node holds the memory location of this one inside of it. It says my next node is this guy. So since now that I don't have any words that I have to draw right except for head, I can erase this and actually draw what a linked list might look like. A smaller more reasonably sized linked list. Something like this. Right? And so on and so forth. Right? And so this list is a linked list of 4, right? The dot next row over here is this, the dot next row over here is this, the dot next row, this one over here is this one, right? These all hold the location. Each of these items hold the location of the next item in the list, right? We keep track of the first one called head. Optionally, and I don't do this for the singly linked list I coded up, although I could have, but I do it for the doubly linked list I coded up. We optionally can keep track of a node called the last node in the list, which we call the tail, right? So that's essentially all we know about the list. We know where the first item is and the last item is, okay? So now why do we do these things? Well, the linked lists have some very interesting advantages despite being scattered throughout our memory. The first advantage is that it's very easy to add new items to the head or the tail, assuming we know where they are, right? Adding a new item to the list is as easy as this. Create a new node to hold the new item in, okay? The next thing we do is we connect the new node to the current head. And then finally, we make this new thing we've connected the head of the list, right? And actually, that's a constant time operation because essentially think about what we did. We essentially drew a box and pointed an arrow. It didn't care how big the list was already. All right. Now this last item in the list, the tail, which I'll just go ahead and just give myself a bit more room to work with, right? That last item, the tail, now that points, what is its next? It's nothing. It's null. Its next is null. Which could be represented by leaving it blank, which is what I typically do. Or if you prefer, you can draw an arrow and just have it leading to nowhere. Or you can have an arrow and have it point to X to indicate that there's nothing following it, right? But any interpretation of that is fine. Okay? So, and adding to the tail is adding a new item to the end of the list is also fairly straightforward. You just create a new item, you attach the tail to the new item, and then make this new item the tail. So that's the advantage is that adding new nodes into this, or moving nodes from the front or the end, very, very fast. Disadvantage is that adding anywhere else, just like a linked list, just like the array list, is kind of terrible, actually. Because we only know where the head and tail are, this actually takes a long time to iterate through. Like, if I say, I'm going to go ahead and put their index numbers over here, 0, 1, 2, 3, 4, 5. If I wanted to get index 3, I have to start at head, go to index 1, go to index 2, go to index 3, right? I have to follow the .next pointers. I just can't jump there like you can with an array. I actually have to manually follow the arrows to get to index 3. As a result, if I want to add anything into an array list, to a linked list, it's a bit of I first have to say I wanted to add an item and I wanted it to be the new one. I wanted to add it at index 3. So what I'd have to do is add this item and create a node to add this item. Okay. Then I have to go and find this node, the node before the place I'd like to insert it. Okay. And then I attach this node to this one, and then I attach this over here. Okay? And then everything just renumbers itself automatically because indices adjust kind of automatically. Okay? But the point being is that the actual inserting of the item once you find it is constant time, but if we have to find the location to insert it, it takes O of n time. Similarly, getting an item from an index in a linked list is O of n time. Replacing a node is O of n time because we actually have to get to that node, assuming the end is not the first or the last one. Now, so really linked lists are really good if you're just adding and removing things from the front or the end. Or if you have to basically simulate something that needs to be sliced up. Because lists are really good at being sliced up because I can essentially make this part of the list the front of the list by doing a couple of interesting moves. Right? I can find this over here. I can take our end, point it to the very front of the list, right? And then delete this pointer and make this guy the new head. Assuming I keep track of everything properly. And now, basically, I completely reordered the list just by cutting a couple of cords, so to speak, and adding a couple more arrows. So they're really good if you want to create small slices of stuff, right? Creating small subsections of stuff. So there's a couple different types of linked lists, which are fair. Actually, before I go on, I'll go on to this. So there's a couple different types of linked lists, which are not, they're not all that different. And we were just tackling what we call singly linked lists, where basically each node has a next, right? It just keeps track of the node after the next. A doubly linked list, on the other hand, each node has two links. One keeping track of the next node, and then a doubly linked would also be keeping track of the previous node, which I abbreviate as PREV, just simply so I could also keep 4 letters, right? So you keep track of the things both in front and behind. Now, adding a node to a linked list or removing a node to a linked list isn't too complicated. Essentially, you deal with, if you're keeping track of the head and the tail, you deal with 5 cases. If you're keeping track of just the head, you only have to deal with 3 cases. Essentially, you have to, as you'll see, keeping track, in those cases are, is my index out of bounds? Am I adding the very first node or removing the very last node from the list? In other words, was the list currently size 0, or if I'm removing, is it going to go to size 0? Adding a new head to the list, adding a new tail to the list, and then the last case is anywhere else. Those are your 5 cases, and they work. And if you arrange your linked lists, the adding and removing for a linked list, it works out fairly straightforward and might not. So I've given you until Friday next week to do it, which will coincide with basically being done with the exams, with being done with your first exam, because I think we'll do our first exam next week. However, if you get this done and if you guys, like, if the vast majority of the class is done with this, I'll throw some more homework on linked list up, which can be like extra credit or something like that, you know. So, because might as well give you guys some extra credit opportunities. So, the type of linked list you'll deal with for the homework, which I'll go over in a bit, is a circular linked list, where, and I'll go ahead and just simply make it singly linked, where it's rather than the first node, where rather than pointing to just null, the last node points to the first node. And that's all that the circular linked list is. It just basically means that we can just keep looping around the ring. All right, so what is your homework? And then we'll talk about the specifics of the exam. So your homework is a math problem called the Josephus problem. Okay? It's a very old, or at least well-known math problem. So, home, teaching, destruct, assignments. And I've given you some starter code. Right, and this is called the Josephus problem. And let me just make sure that I'm recording the right thing. Yep. Okay. So it's named after named after the historian Titus Flavius Josephus, who lived from 37 to 100. Anyway, he participated. He was a priest of the Jewish religion of the time, and he participated in an uprising against the Romans. This ended exactly the way you'd expect every single other uprising against the Romans went, which was that they lost horribly. The Romans were really good at putting down revolts during that time. Okay. So anyway, he became a war band leader, and during that time, he basically got himself. He was on the losing end of like one of those last battles, and him and the other soldiers decided that rather than essentially being captured and taken as Roman slaves, they would commit mass suicide instead. So we don't know the precise method, but we think we do, which is we'll get into in a second. But essentially, they drew lots, and whoever drew a lot, they would basically be killed by the other soldiers. So anyway, so we start out with all these soldiers, and then they whittle themselves down, and eventually it's only Josephus and one other soldier who decide that maybe this was a terrible idea, and actually having a life that was terrible was better than no life whatsoever, so they became a slave. Eventually, Josephus got his freedom. I think it was something along the lines of pretending he had the power of prophecy and prophesizing that his master at the time, which was some general, would go on to win some great battles. Spoiler, people who are good at the generaling ability are generally pretty good at battling and remain generals. So thanks to his amazingly accurate predictions, he got his freedom. That's at least if I'm remembering my Wikipedia read correctly. But anyway, he got his freedom, and then he went on to write a number of documents about just history of that time. Especially since this date, 37 to 100, that's basically this gives us a lot of insight into early Christianity, the stuff he wrote about. And also how basically, because at that point you still had people who were considering themselves Jewish, right? So it was actually very interesting to see how these religions separate themselves. But it gives a lot of insight into the religion of the time and how early Christianity forms. So anyway, so he's an interesting historical figure. Check him out. His stuff is like, you can find his stuff freely on the web because it's surely out of copyright by this point. So anyway. The problem is basically, so given we have these soldiers, right, and they're all committing mass suicide, right, say you think that's a bad idea. So where in the circle where in this process do you need to be so you are the last person remaining, okay? So the idea here is that the way we think that these soldiers off themselves is that they got into a circle and they counted around, and basically they would count around the circle in some predetermined number, okay? So basically look something like this, and I'm going to go on to the board again, right? could try it to solve this problem mathematically, but it turns out that the mathematics behind it are actually quite hideous, and they're exceptionally hideous, in fact. So anyway, here's the circle. Here's the circle. Let's say, and I'm going to start from 1 rather than from 0. 1, 2, 3, 4, 5. Right. So say we have 5 soldiers, and the way they decide which one leaves the circle is that they're going to count off every second soldier in the circle and remove him from the circle. So the way this works is that we go 1, 2, remove this guy. 1, 2, remove this guy. 1, 2, remove. 1, 2, remove. Right? We're skipping over everybody who's already been removed. So in this case, you'd want to be soldier number 3 if you wanted to survive. Okay? So the Josephus problem says for a ring of size n and a count of size k, where's the safe place to be? Now, what's a count? That's basically how many soldiers we skip every so often. 1, 2, 3, 4, 5. Right? Say our count in this case is a ring of size n, but our count is going to be 3. It would be 1, 2, 3. So it would be very bad luck to be soldier 3 that time. 1, 2, 3. 1, 2, 3. 1, 2, 3. So 4 would be the person you'd want to be, right? So the Josephus problem is given ring of size n, count of size k. Who is the last soldier remaining? Right? So yeah, real life applications right there in computer science. Yeah. Yeah. What? So this is a fairly famous problem. Let's go ahead and check Wikipedia on it. I did say I think I did mention you can check out Wikipedia if you wanted to check out the problem in a bit more detail. I'm not sure if I said that on there, but you definitely should. Josephus problem, right? The Josephus problem. All right, so let's go ahead and take a look at the problem. Right, so here's so the solution to it. Right, here's the general case is what we're solving. So the safe solution, the safe location to be in if you in a ring of size n and a count of size k is this equation over here. So so it involves a recurrence relationship and hideous mathematics. So yeah, it's messy, right? Notice that basically it's saying g of nk is g of n minus 1k plus k mod n, right? So it's saying that basically that it's a recursive problem. Now if k is 2, which is the most common application of the problem, it actually has some really nice math behind it, but again, so what we're doing here, rather than trying to solve it, we're going to not solve it mathematically. Instead, we're going to simulate it. That's how we're going to do it, because the math is ugly. And sometimes it's just easier to simulate something. And I mean, all you'd have to do to solve it is just write this equation in, right? You just have to write this equation in. That would be that. Very easy homework. So no, instead we're going to simulate it. I hand you this code, called, the circular linked list, that you have to implement. So I give you a head and a tail, and then the size. I give you a constructor, and then I tell you, here's what you need to finish. I have a get node method, which, by the way, you can get from my other videos. It works the same in a singly linked list, a doubly linked list, and a circular linked list. The add method, this one you just have to swap this to true instead of false. And then the real work is actually doing the add method and the remove method and handling all the cases that I listed out and doing them in that order. So just simply follow it. If you follow along with the videos, it's actually not too bad of a problem. And the other big thing is to remember, since it's a circular linked list, you always have to make sure that if the head or the tail gets changed, you have to make sure that the tail always points to the head of the list. I build you something called I also give you something called an iterator, which allows you to move through loop through the entire circular linked list without having to worry about like going out of bounds or remembering to go around it. This iterator handles it all for you. I would just simply read how it works. It only has it has 3 methods in it. It's a private class inside of this guy. And it makes the solution fairly easy. And I give you a node. Now notice that the node is a private static class inside of your linked list class, right? This is because the singly linked list has a node, the doubly linked list has its own private node, and the circular linked list will all have a node. So we just want to make sure that, and the private static class means that it just exists only inside of this class, and that way it's not going to interfere with the other nodes. The other classes aren't going to get confused as to which node to use. And then I give you a main method to work with. So I give you a lot of code to begin with. And I found that, I've given you a bit of a long time to deal with this, but, I find that I had a different problem in mind that I wanted to do, but I didn't have time to do a write-up for it. Otherwise, this is a fairly good problem, I feel. All right. So this goes over. So your homework will go over circular linked list. So now, with regards to your examination, right, on next week, right. So you guys will be taking an exam next week. It will be taken in your lab period. So you've got until next Thursday, I believe, right? You guys got until next Thursday to take your exam. You will be getting a practice exam on basically Thursday, I think, this upcoming Thursday. So you have a week worth to look at the practice exam. It will be a very good representation of the actual exam. And it will cover basically all of chapter 2, basically all the way through linked lists, okay? And one of the big things you're going to have to do, as I mentioned here and I mentioned in the videos, and I'll mention it every time that this comes up, one of the questions I give you on the practice exam and will be on the exam is you need to be able to compare and contrast linked lists to array lists. How do they perform? That will be worth about 20 points. So, there you go. 20 points of questions going into the exam. So, but there'll be questions about essentially dealing with essentially how do we write list methods like we do it in chapter 2. Like we did for assignment 2, and then how do you build stuff specifically with linked lists, right? How do you manipulate things with linked lists? Let's see, the last thing I want to say on that with regards to that is that you'll probably be able to, I think you'll probably end up bringing in a cheat sheet, single-sided, 1 page. Sorry, not single-sided, double-sided, 1 page of notes. And that can be handwritten or typed or microfleach or whatever. So, kind of like a really, really tiny typeset thing that you'd probably need a microscope to read. So basically, if you can format it, basically I don't care how you put your notes in, so long as it's on a sheet of paper, right? And if you want to, and if you need to, and if you are very interested in finding out how far you can stretch those rules, I would love to see how far you can stretch a single sheet of paper. So, okay. Yeah. Do I need to put on the restriction that's 8.5 by 11? Yes. 8.5 by 11, front and back. All right. So we can go ahead and get to work on with the remaining time we have. And again, I'm not going to be here on Wednesday, but your TA will be.